identities, the main thing that you're going to do with identities is prove them. Prove identities. But you also should be able to verify just for one single angle measure. When I prove for any angle measure. Verifying is just picking one angle and also showing that it's true. And non-permissible values is sometimes, many times, every identity will have a non-permissible value. So just being aware of that, getting a little more practice with our non-permissible values. So let's look at the first one. Our first identity, and we'll go in order. It says for each one, and there's only two here. For each one, prove, verify, state any NPV. You can go in any order that you want, but let's do the prove first. So to prove an identity means I can't use any angle measure, right? I have to do it totally theoretically, and my goal is to show that the left-hand side is identical to the right-hand side, okay? So usually we do a T-chart, and the T-chart forces you to separate the sides. You can't, it's not solving an equation, so you can't move terms over from one side to the other. I think I'm going to start with the left-hand side again. Just because there's more for me to work with on the left-hand side, right? So on the left-hand side, I see secant divided by cosecant, and I have to convert that to a tan. So I have a reciprocal function divided by another reciprocal function. What would you do first to simplify this to tan? What do you think you would do? Turn it to cos? So turn this to 1 over cos, and then would you do the same thing to the cosecant, Joanna? 1 over sine, right? And then I've got two fractions that I can multiply. Instead of just leaving them division, I'll put them in their multiplication state. So that means multiplying by the reciprocal of the bottom one, which gives me sine over cos, right? So just to show you can work both sides, I could also say, okay, my right-hand side, tan of x is sine over cos, right? You could do that too, or you could just keep going and call this tan, and at that point I say left-hand side equals right-hand side. So that's proved. I've proven an identity. Now let's see what the difference between proving and verifying is. To verify means, we still use this process, right? I've always used that T-chart for verifying in the past as well when we're checking our answers, so I'll do the same thing. But this time it's a verify for, and they give me actually a solution, one of these solutions. Okay, so it looks like a solution. They're saying x is 30, so what do we usually do with verification? We substitute the 30 in wherever I see x. So I have to show that secant of 30 degrees divided by cosecant of 30 degrees equals tan of 30 degrees. Okay, so this is where our knowledge of the unit circle comes back into it. Now, at this stage, this is a homework exercise or like a class lesson. You could have your chart in front of you. If you can't remember, does anyone remember what tan of 30 degrees equals? You can look at your chart. Square root of 3 on 3, I agree with you. Square root of 3 on 3. Or 1 over root 3, right? So that's good knowledge, Joanna. Now I have to see, can I get that, those values, will they equate root 3 on 3? Well, let's see. Secant of 30 degrees. You might have to think, like in your head, you're thinking, okay, asking for reciprocal function is kind of hard, right? But 30 degrees is here, that long skin, that kind of low skinny triangle. This is where cos is bigger than tan, right? X is bigger than. So that means my cos of 30 is this value, sine of 30 is 1/2. So that tells me, and again, maybe you don't need to write your notes, but these are all the thoughts going on inside my head, right? That means secant of 30 is 2 over root 3, and cosecant of 30 would be just 2. Okay? These are the values I need. So I have secant of 30 is 2 over root 3 divided by 2. So then that becomes 2 over root 3, I'll just do this, times 1 over 2, right? It was being divided by 2, so times 1 over 2. Okay, my 2's cancel nicely, and I have 1 over root 3. I see a lot of similarities, but these aren't the same, or are they? How can I make them look exactly the same? What's that process called when I get rid of the root sign on the bottom? Just rationalizing, right? So sometimes we have to do that. Let's see if rationalizing, because this is rationalized, let's see if rationalizing gets me the same. And it does. Left-hand side equals right-hand side. Now we knew that when we proved it, we're proving it for any angle measure. And I proved that just for a specific angle measure. So this isn't really a proof, this is a proof. This means any angle will work as long as it's not a non-permissible. Any angle works here. Here I just kind of showed you 30 degrees works, so this is an example of that. But if I just left it here, this isn't enough to say that it's a proof. This is just showing you it's true for 30 degrees. When I prove it generically, that means it's true for any angle. Okay? But we also have to be aware there's non-permissibles. So take a close look. What would my non-permissible values be? Do you see any? Well, of course I see fractions here, right? What are my non-permissible values here? Cos and sine, right? So this is really a 1 over cos, right? So cos x can't equal 0, right, Rahel? Sine x can't equal 0. And here, tan would be sine over cos, but I've already got that one identified, right? Okay, so where does cos equal 0? 90 degrees and 180, right? Or sorry, 270. And sine equals 0 at 0 and 180. And I'm just going to put in words here and all multiples of above. Because I kind of ran out of room, right? Normally I would put plus 360k, because that means any multiple. I guess I could also have used the words and all coterminal angles to those two, right? So those are the 3 things for now that you'll be doing with identities. Proving for any angle, proving for one specific angle, and being aware of the non-permissibles. This is really important because lots of spots on the unit circle have non-permissible values for certain trig functions. Cos and sine are the only trig functions that have no non-permissibles in and of themselves. As soon as they are used to find the secant or cosecant, then we have to be aware of where cos and sine are equal to 0, because they can make or break if an identity is provable or not. So basically what we're saying is this is a proof except for where the angles where cos or sine equals 0, except for like the 90 degree, all the quadrantal angles, right? The 0, the 90, the 270, or 180. This is true. For any of the quadrantal angles, we can't even show this is true because there's the undefined values. Yeah? Okay, let's take a look at the next one. Prove, verify, non-permissible value. So, I'm going to get you to set this one up, and I'll be right back. I think I left something in the library. Make a decision on what side you're going to start with. What side did you choose to start with? Left or right? I think so too, because there's lots to work with there, right, Rahel? So, what was your strategy, Rahel? Did you start converting things to sines and coses? Okay. So this would be 1 over sine minus sine, all divided by cos over sine. Agreed? Now what? LCD here? So what's the LCD? Rahel says she needs an LCD for the top. Why does she need an LCD for the top? And ultimately, I guess what I'm saying is you want to combine these two, right? Does everyone agree with that strategy? Combine the two on the top? Because if you think about it, I'm taking 1, 2, 3 trig functions and I'm converting into one. So somehow or other I have to merge them all together, right? So Rahel's first thing, she's going to merge these two and her LCD would be sine. Agreed? Okay, so what do I have here then? I'd have a 1 over sine minus, if the old denominator was 1, so if I want to make my new denominator sine, I have to multiply the top by sine as well, and I get a sine squared. Agreed? Okay, that's the biggest leap, I think. If you can figure out that, that's awesome. Now I have a cos over sine. That hasn't changed, right? Everyone on this same path? Because there are more than one ways to do it. Is this how you approached it too, Joanna? Or did you do something different? There's different ways to do it. Did you do something different? Okay. So I'm gonna actually, well, let's proceed with this way. Then I want to ask some different approaches. So then I guess now at this point, Rahel, I can do this, right? 1 minus sine squared over sine, and then it's going to be multiplied by the flip of this. Then I'll have sine over cos. And then what we see here is I've got canceling that can go this way, right? And I have 1 minus sine squared over cos. And now I'm stuck. Now what? Do you remember from yesterday our Pythagoreans? 1 minus sine squared is cos, right? So that's what Eileen said. She's going to convert that 1 minus sine squared to a cosine. So this becomes cos squared over cos. And then bottom cancels 1 on the top, right? And that's cosine. So left-hand side equals right-hand side. Excellent. All right, that's one approach. I know Joanna did a different way. Dennis, did you approach this a different way as well? You did it the same way here? And Eileen, you did it the same way, right? John and Ibby, you did it the same way?
No,
Different? What did you do?
Well, when I did the subtraction first, which is I get 1 over sine minus sine theta over 1. Then I did 1 minus sine squared theta divided by sine theta. So 1 minus sine squared, I changed it to cos.
Oh, right away.
Squared theta divided by sine.
Okay, so basically to say very similar, right?
Similar, but I
Yeah.
just
You kind of simplified it in a different spot, maybe.
yeah.
John, what about you? Did you approach it different or same? Similar? I'm curious. Joanna, what did you do? Please tell me or show me, because I'm thinking there's another way that might even be. So you called that a tan, right? Yes. Okay, I was wondering if anyone did that. Okay, watch this, you guys. How about this? So we have cosecant minus sine. Tell me if you think this is a strategy that you might employ too. So you know, the one thing for sure is we know that there's got to be a heavy duty amount of canceling going on, right? If I'm going to take all of these trig functions and they all simplify to cos, there's going to have to be lots of canceling. This is what Joanna did. She recognized that, you know what, I got a cotan on the bottom. What if I move the cotan up? What happens when I move cotan up? The reciprocal of cotan becomes tan. So basically she moved that to the top and got rid of her fraction right away. So just bear with me. Agreed? She just moved the cotan up. When you move it up to the top, it becomes tan. Okay, now we're ready to do, you actually did your sines and coses right away, but I just wanted them to see that moving cotan up gives me a tan. Okay, tan is sine over cos, right? And cosecant is 1 over sine, and then I have a sine. All right, so what happened? Those brackets mean multiply, right? So I could do sine over cos times 1 over sine, and then minus sine squared over cos, right? Is this what you did, Joanna? Okay, so then cancel, and I get 1 over cos minus sine squared over cos. Okay, I have the same denominator, right? That worked out nice. So then I get 1 minus sine squared over cos, and you still have to recognize that 1 minus sine squared is cos squared. Cos squared over cos, cancel, cancel. Cos equals cos. So there's lots of similarities, but kind of a little different at the beginning too, right? You'll always end up, if it's an identity, you'll always end up proving it. You just might take different paths than your colleagues, right? So don't get frustrated with identities. If you get stuck, and today I'm going to show you a few other hints, if you get stuck, just think of an alternate route out, or just start converting again to another trig function, right? And in the end, one of the foolproof strategies, like we've mentioned before, is just go back to convert everything to sines and coses and see if that helps you. Okay, let's keep going for this one. Let's verify for pi on 4. Okay, so let's verify this for pi on 4. We're back to verifying, not just proving. So that means I have to show that, okay, I am showing that, oops. Pi's on 4s are a little easier to remember because they have those duplicate values, right? So I'm showing that cosecant of pi on 4 minus sine of pi on 4 divided by cotan of pi on 4 all equals cos of pi on 4. Neville, you want to grab one of these? We're just working on this. And at some point, you're asked to go down to the counsel's office and talk to John. There's a message for you. Okay. Okay. You remember your cosine of pi on 4? What's that one? Abdullah, you remember cosine pi on 4? Root 2 on 2 or 1 over root 2? Okay. So cosecant and sine and cos have the same value. So for cosecant, it would be what? 2 over root 2 minus root 2 on 2, right? All over, what's cotan of pi on 4? 1. So that's kind of nice. Okay. So all I have to do is worry about these two. So my LCD would be 2 root 2. Okay, so for this one, I'd have a 2 root of 2, 2 root of 2. Okay, so for this fraction, I have to multiply by 2, so that gives me 4 on top. For this one, I'd have to multiply by root 2. So the root 2 times root 2 gives me 2. So then I get 4 minus 2, I get 2 over 2 root 2. So let's rationalize again and see what happens. So I'm going to multiply by root 2 on root 2. And these guys cancel out, right? So I just have my 1 here. So that gives me my root of 2 over 2. Perfect. So left-hand side equals right-hand side. So I've shown that it's true. I've verified for pi on 4. What we did first is we actually verified for everything, for every possible value. And what are my non-permissibles? So someone tell me what my non-permissible values are. Yep, sine theta can't equal 0, right? And cotan can't equal 0, right? But that's where sine equals 0 again, right? So that should be the same. And then here, nothing over here. So cotan is cos over sine. So again, that's where sine equals 0. So it should be the same spots, right? And that happens at 0, 180, and all multiples, right? And where does cotan equal 0? Same spots, right? And all multiples. Let's check our cotan out again, though. I'm being lazy and I'm just writing that out because I'm running out of room. Let's look at our unit circle again, though. I think I have one. Okay, so you know what I'm going to do? I'm also going to do this too, because those reciprocal functions are tricky, right? And I think in your book, remember when we have to do all our charts? I think in our book, when we had all of our charts written out, yeah. So it's only when there's zeros and ones, right? So let's do a real quick shortcut. So I'm looking at one of our tables from the textbook, and you might have this on your unit circle chart. So for all, it's only at the quadrantals that we have to worry, right? So sine equals 0 at 0, 180, 360, etc. Cotan is undefined at 0, 180, 360. Same spots again, right? And cotan is cos over sine, so it makes sense that cotan is undefined wherever sine is equal to 0, right? So these ends up being the same spots, the undefined values. So we've actually covered these non-permissibles fit for both of these, right? Yeah? Okay. Okay, so that's the difference between proving for one value, proving for all values, and that's called actually the word proving. Here we're just verifying for one certain value, and just be aware of your non-permissibles. Agreed? Now if you flip on to the other side of that paper that I gave you, this is what you're going to work on for the next part of the class. Proving identities. So there's 20 here or 18 here. There's not enough room on your paper. You have to work on lined paper or extra paper, and I can give you lined paper if you want, or blank paper. So what you're gonna do is you're gonna follow through, and I think we've seen this one already, right? Cos times secant, so cos times 1 over cos would be 1. But I suggest you setting them up in T-charts. You can't cross terms, right? You're not solving an equation. You can work both sides, but you have to work both sides separately till they end up being the same. Now there's some trickier ones here. I'm going to give you time to play around and work and see what you come up with. Remember, there's more than one way to approach an identity. But the other thing I'm going to hand out to you, and I did it on a separate paper so you can have this for a piece of notes that you can kind of keep referring to. And I wanted to do it on a separate paper so you didn't have to keep flipping back. I provided a few little tips, okay? So I'm going to give everyone these as well. When you get stuck, refer to this helper sheet and see if that helps you out of your little rut that you're stuck in. So let's just read some of the helpers I gave you. So once again, just some words. Trig identities are equalities or equations, truths involving trig functions. They're true for all values of the variable, as long as they're not the non-permissibles. Identities can be used to simplify expressions, to prove new identities, and to solve equations. Okay, we haven't got to that part yet. That's the second part of this unit. All we're doing is proving identities. There is no one specific way to prove identities. Below are some tips to help you when proving identities. Remember to work separately with each side. There is no transferring of terms from one side to the other. That's why the T-chart's nice, because it forces you to stay on either the left or the right. So here's some tips. Start with one side of the equation and try to reduce or simplify it to match the other by substituting various identities. For example, if I have a tan, I might try sine over cos, right? Or tan is also 1 over cotan, whatever you think might fit the situation better. It's usually a good idea to start with the more complicated looking side and reduce it to the simpler side. When you start working on one side, keep looking at the other side for ideas that might help you. Always keep in mind what your goal is, right? You can simplify each side of the equation separately, meaning you can work on both sides. You can't cross over. If you can reduce each side to the same expression, that's also proving, meaning you can work on this side till you get to a certain point, and if you get stuck and you can't figure out where to go anymore, start working on the other side, simplifying, and maybe you'll arrive at the same spot. That's proving as well. Other tips. Factor. That's why factoring again was so important in grade 10. Factor when possible. Factoring will take the addition of two terms and turn it into multiplication. Multiplication's great because then you can cancel. You can cancel when terms are multiplied together. You can't cancel when they're added. So factoring is great. Use LCDs. We already saw that, right, Rahel? That one that you were verbalizing for us. You found the LCD and pushed two fractions together. And that way we could do some heavy-duty canceling. Okay, we haven't seen one of these yet. And I'm going to identify, but multiplying both the numerator and denominator by the same expression. Often this means multiplying by conjugates. And this also can create a Pythagorean identity, which can help you to substitute other identities. So that's a really important one. I'm going to give you some time just to work. They're sort of set up. The easier ones are at the beginning, then they get more complicated. When we get to one that everyone, I don't want to help you if you don't need help, right? But if everyone kind of gets stuck on the same one, maybe we'll take a look at, and it could be one of these. If you get stuck, last resort, or maybe it's your first resort, switch everything into sines and coses. They can all be written in terms of sines and coses. And that can usually help get you out of a rut. Back to this one, does everyone remember what the word conjugate means in math? You saw that in rationalizing. What do you mean by opposite sign? We do conjugates of binomials, right? So when you guys were rationalizing, you might have had something like this. So the conjugate would be your terms stay identical, it's just the opposite sign. It's like the factors of perfect square, right? Those are conjugates. X minus 2, x plus 2. So a conjugate in trig might look like this. Sine theta plus 1. What would its conjugate be? And when I said that conjugates are used in perfect squares, that's exactly why they're used, because what happens, they end up multiplying out to a perfect square. What happens if I have these guys? So I get minus sign plus sign minus 1, right? Difference of squares. What about this guy? If I have 1 plus cos, I'm going to multiply it by 1 minus cos, right? And look what happens. A couple things happen. Okay, I know it's a difference of squares, so then I multiply through and I get 1 minus cos squared. As soon as I get, by multiplying by the conjugate introduces a squared term. In trig, those squared terms, when you get a cos squared or sine squared or a cotangent squared or secant squared, those are called the Pythagorean identities, right? You've created a Pythagorean identity. So what's 1 minus cos squared? Sine squared. Which is really powerful. Because I took this one binomial and I converted it into one square term which I can cancel out. Now remember, when you're multiplying, I'm only on one side of the equation, right? So I don't know, whatever I had. Let's say I had a sine over a 1 plus cos. And I'm trying to prove it to my right hand side, and I don't know what my right hand side is. There's not much to do here, right? These are tough. When you get a tough one like this, there's nothing, it's already in terms of sines and coses, right? So I can't use that fallback strategy. There's nothing to do. And I don't have any square terms. Square terms are ideal in identities because I can go to my formula sheet. Without any of these guys with squares in them, I can't do anything. I'm stuck. So I need something super creative. Multiply by a square partner, right? So that means I want to multiply him by 1 minus cos. Just remember in identities, just like in other math, you can't do something to the bottom without doing it to the top. This is okay mathematically. If I just did it to the bottom, it's not okay, right? Why is it okay that I multiply by this funny looking fraction? Why is that mathematically sound or mathematically appropriate to do?
It's not making any change because it becomes 1.
Yeah, I'm just multiplying by 1, right, Abdullah? 1 minus cos over 1 minus cos, that's just 1. It's a fancy form of 1. It's the form that I need to move forward. But am I changing the value of this? No, because I'm just, when you multiply anything by 1, you're not changing what you were given. Okay, but it's a very, very interesting way to think about math and to approach math because it gets me out of my hole that I'm stuck in. Okay, I'm just going to leave the top in factored form because factored form is great for canceling. And what happens on the bottom? 1 minus cos squared, which is sine squared, right? And I already had this guy. When in doubt, leave things in factored form, like we did here. Okay, so then I can cancel, and then I have this 1 minus cos over sine, which I hope was the right-hand side. And that's probably what it was. They probably gave you this for the right-hand side. Right? So we started with this. They were saying, show that this is equal to this. Oh, we just did, right? By just multiplying by its. When I say conjugate, most people think of that rational section, but think of it just as the perfect square conjugate, because that's what you're doing. You're just creating perfect squares. Remember that one. So those are the tough ones. The tough ones are, it's already in sines and coses. There's no squares in there. So you can use a fancy form of 1 to create a square. Maybe?
What do you for the 1 minus cos
Those don't occur every day, but those usually are the toughest ones for students, because it feels like if you don't have any of those strategies, kind of the more sophisticated strategies, you look at all the hints I gave you and you're like, well, she said turn it into sines and coses. It's already in sines and coses. She said look at the formula sheet. There's no formula sheet. I can't turn sine into anything. Sine is just sine. I can't turn cos into anything. Cos is just cos. So what do? You create your own difference of squares. And then that creates a Pythagorean identity for you.
How did you get the 1 minus cos squared is sine squared?
Oh, this one?
Yeah.
That was that very first identity we learned yesterday. Sine squared plus cos squared equals 1. Okay, so that's our equation of the unit circle. So remember those spots on the unit circle? This was x, y, this is 1. X squared plus y squared equals 1. But when we're talking trig, if I identify those trig ratios not as sides of a triangle, but as cos of the angle and sine of the angle,
Yeah.
this is for sure true, but this is also true. That cos of theta on a circle with radius 1 is going to be equal to x over 1. Sine is equal to y over 1. Then you say, okay, well, on a circle with radius 1, cos squared equals x, sine squared equals y, or sine equals y. So this would be y squared plus x squared equals 1, right? Or y squared plus x squared is also equal to sine. If sine is equal to y, cos is equal to x. Sine squared plus cos squared equals 1. Okay?
Yeah.
This is your key identity. Just remember that. Now, from here, I can take this and I just manipulate all the, if there's 3 pieces in a formula, there's 3 ways to write the formula. I could say that, okay, if I want to solve for sine squared, just move the cos over is equal to 1 minus cos squared. If I want to leave the cos squared isolated, I move the sine over. Okay? So those are super powerful. They come from sine squared plus cos squared. So then I say, hey, I have 1 minus cos squared. But what if I substitute sine squared in there? That would help me out. So that would mess up things.
I see. And it's the same value.
It's like if I had an identity and I had a tan on the left hand side, tan equals blah blah blah. I don't know what tan equals. I can say, hey, I don't like tan. I want to say, I'm going to call tan as sine over cos equals blah blah blah, because that might help me out more. I'm just replacing tan with sine over cos. I can, because this equals that. It's an identity. I can replace this with this because it's an identity. Now you know it's your identity because we kind of, sort of, in some really small way, proved it way back when that sine squared plus cos squared is 1. You're allowed to accept it as identities because it's on your formula sheet. So because it's on your formula sheet, you know it's been proven. You can go and reference math books and you can look back and you can really delve deep into the proofs if you really want deeper proofs or more proof that it is true. But you don't have to prove those identities. Years ago, there was lots of proof involved and you would have to prove certain things, but not anymore. So whatever's on that formula sheet, you can just use without proving and know that it's true. But know that you can go back to math books when you ever have time one day and you can look at the proofs themselves